Welcome back, design junkies, to Mechanical Engineering Made Simple. Today, we're going hunting for a silent killer, an unseen enemy that lives inside our machines. We're going to talk about tolerances, these tiny, invisible details that can mean the difference between a machine that runs forever and one that just shakes itself to pieces.
So let's start with a mystery we've all seen. You've got this powerful, beautifully designed piece of equipment, a motor, a gearbox, whatever, and one day it just starts to shake. It gets hotter and hotter, and then, boom, catastrophic failure. What is going on there?
The signs are always the same, right? It kicks off with a vibration you can feel in your teeth. Then comes the heat. Bearings start to glow. The lubricant just gives up. And the finale? A complete, total, and usually very expensive failure. These aren't just random accidents, you guys. They're symptoms of a much, much deeper problem.
To really get to the bottom of this, we've got to look past the broken parts and dive into the physics of how things are actually made. This is where we uncover the real root cause, and trust me, it's hiding at a microscopic level. Okay, so every single mechanical system has this natural tendency to oscillate. It's just a simple back and forth movement. A good way to think about it is like a guitar string, You pluck it, it oscillates, it makes a sound. But when you take that same idea and put it in a high-speed machine, if that oscillation gets out of control, it morphs into the monster we call destructive vibration.
So what's causing all this? Well, here's the twist. It's almost never one big, obvious crack or flaw. The real culprit is the combined chaos of countless microscopic imperfections. Tiny little errors in the shape of a shaft, the size of a hole, the location of a bolt, all of them add up.
And in engineering, we have a name for these places where the gremlins hide. We call them features. A feature is just any physical bit of a part. They could be a flat surface, a little pin, a hole, a slot. This is the battlefield where precision is either won or lost.
So, how in the world do we control this chaos? We know we can't make anything absolutely perfect. So clever engineers came up with a system to manage it. A system of standard fits designed to bring some order to the beautiful mess of manufacturing.
And at its heart, this system really boils down to two basic relationships. On one hand, you've got a clearance fit. This is simple. The shaft is always a little bit smaller than the hole it goes into. This is for anything that needs to slide or spin freely, like an axle and a bearing. But on the other hand, you have an interference fit. Now this is wild. The shaft is actually made bigger than the hole on purpose. You have to use a press or heat and cold to assemble it, and it creates this incredibly strong, locked-in connection. Think of a gear that's permanently fixed to a motor shaft.
And this idea is what brings us to the star of the show, tolerance. A tolerance is simply the total acceptable amount a dimension is allowed to be off. And let me be clear, this is not a suggestion. It's not a nice to have. It is the absolute ironclad rule that decides if a part is good to go or if it's headed for the scrap bin. No exceptions.
Let's make this real. Here's a snippet from a standard engineering chart. Let's say we need a shaft, somewhere between 10 and 18 millimeters, and it needs to spin loosely. The chart might call out an H7 hole and a G6 shaft. Okay, so what does that gibberish mean? It means the hole can be up to 18 thousandths of a millimeter too big, but no smaller. And the shaft, it has to be between 6 and 17 thousandths of a millimeter too small. By following these rules, you guarantee there will always be a tiny gap, a clearance of between 6 and 35 microns. It's guaranteed to spin freely. That's the magic.
But just controlling size isn't enough. What about the shape or its location? For that, engineers needed something way more powerful. They needed a whole new language dedicated to precision.
And that language is called geometric dimensioning and tolerancing, or as we all know it, GD&T. It's this universal system of symbols you see on blueprints, and its whole purpose is to kill ambiguity. It makes sure that a part designed in Munich can be perfectly understood and made by a machinist in Minnesota with zero confusion.
The basic building block, the fundamental sentence of GD&T, is this little thing called the feature control frame. Just think of it as a little instruction box. It holds the rule you're applying, how much wiggle room you have, that's the tolerance, and where you're measuring from, which are the datums.
So let's look at a few of these symbols. First up, an easy one, flatness. It's simple but super important. All it does is create a zone between two perfectly parallel imaginary planes. The entire real surface of the part has to lie somewhere in that tiny gap. It's how you guarantee a surface has no weird waves or bows in it.
Okay, next up is position. Now, if flatness controls the shape of a surface, position controls its location.
This is probably one of the most powerful and common symbols in all of GD&T. It basically defines a perfect theoretical spot in 3D space and then says the center of your real feature, like a hole, has to be somewhere inside a tiny little tolerance zone around that perfect spot. It's basically the GPS for a part's features.
Now let's tie this back to our original problem. Check out total runout. This is absolutely critical for anything that spins. It controls how much a surface can wobble or vary as you rotate the entire part 360 degrees around a central axis. This symbol is the direct enemy of imbalance. It's what stops shafts, pulleys, and bearings from shaking themselves apart.
So we've got the system, we've got the language, we can write the perfect instruction manual on an engineering drawing. But now for the hard part. Someone has to actually make the thing. We have to leave the perfect world of the computer screen and get our hands dirty in the machine shop.
Hitting these insane tolerances isn't just art, it's a hard science. Skilled machinists rely on data tables just like this one to figure out the exact cutting speeds. For a piece of medium carbon steel, for instance, they might be running at 90 surface feet per minute. But if they're cutting a really tough stainless steel, they have to slow way down, maybe to 10 or 35 SFM, just to stay in control and not mess up the part.
And even when they nailed the speeds and feeds, machinists are in this constant war against the enemies of precision. They're fighting things like bell-mouthed holes, where the entry to the hole gets flared out. They're battling chatter marks, which are literally the pattern of vibration carved right into the surface, all while keeping an eye on the cutting tool itself, watching for wear that could ruin the part. It's a tough job.
You know, when you step back and look at the whole picture, the physics, the system of fits, the language of GD&T, and the incredible skill of the machinist, you start to realize that modern engineering is this kind of unseen elegance. It's a ballet being performed on a stage so small you can't even see it.
Let's go back to that shaft example from a minute ago. The entire window for air, the total tolerance from the smallest acceptable shaft to the largest, was just 11 thousandths of a millimeter.
Now, to give you some perspective, that is 7 times thinner than one of your own hairs. That is the hidden world that engineers and machinists live in every single day. A world measured in microns, where the gap between a machine running perfectly and a machine failing catastrophically is smaller than the eye can see. This is where reliability is actually born.
And that kind of leaves us with one last thought to chew on. If a few microns, a microscopic deviation, can literally define the life or death of a machine, it really makes you wonder, doesn't it? What are the tiny, unseen details that define success and failure in your world?